welcome to another episode of Launchpad Office Hours. This is number 15, and today is 10th of April, 2024. Okay, so what we're going to cover today, as always, the latest Launchpad developments since last LOH. Then we're going to talk about PostgreSQL high availability topics. So what you need to concern yourself when you're thinking about high availability. We're going to briefly touch on Postgres operator, but we won't go into much detail there because we're aware that not everyone is using Kubernetes. And then we'll talk about Patroni for high availability. We'll touch upon write-ahead logs, replicas, standbys, and clones. And then we'll spend a good amount of time on important gotchas that we came across over time for setting this up. All right, so starting with the general update of Launchpad development activity. As always, we've had new chart versions for GraphNode, Subgraph Radio, Nimbus, Lighthouse, Aragon, and pretty much most of our charts, since it's been a while since we ran an LOH. Here, we want to thank Alexis from Semiotic for his first contribution on GraphNode. And I'll briefly show some of the changes. So what's the major changes in the chart? Let me just exit this. So for the GraphNode, we found a bug around how GraphNode defaults were being applied on top of each other. And then how merge values were being applied as well. So some of them were not. Some of them were ignored. So this is one of the main change for the GraphNode. So improving the overall operability of the way values are grouped together and merged. And then for Launchpad namespaces, again, we have had new stable releases of most of our namespaces. Monitoring graph sealed, basically pretty much all of the namespaces have had new stable releases, but here some really noteworthy changes. So Arbitrum1 namespace has been updated to support proxyd for each one of its nodes. So there is a proxyd classic now and the proxyd nitro that is supported with the Arbitrum namespace. And this is important to know because it is a breaking change into how you set up your Helm release. And another thing that has been added here is per release scaling for Arbitrum. So if before you could add scaling deployments for each one of the releases, now you have an additional field for Arbitrum Classic scaling and Arbitrum Nitro scaling as well. Okay. And then another major change with Launchpad namespaces is we have improved on volume claim template labels. So they were the labels and annotations that existed were not adding labels to volume claim templates. So the PVCs created by stateful set did not have the same labels as other resources managed by the stateful set. So this change that has been added 2 weeks ago fixes that. However, this would cause a breaking change where you would need to manually update labels and briefly scale down your stateful set replicas. Quickly checking the chat. So Vince is saying that he's been making a substreams and block meta Helm chart and the full Firehose Helm that includes both with the new substream changes. That is great. All right, okay. I'll go back to the chat later on because it's distracting me a bit. Okay, so going back to Postgres high availability. When you are thinking about ensuring redundancy of data and operation, and to enable your Postgres to continue functioning despite individual component failure, you want to account for the following So for automatic failover, so you want to automatically switch operations to standby replicas if something happens with the primary database. That's ensuring service continuity. You want to think about data integrity and consistency across your primary and replica servers, even in the event of a failover scenario. And you do that through write-ahead logs and transaction management. You want to think about scalability solutions that allow your databases to handle increased loads by distributing read queries across replicas. Then you also want to have a plan for disaster recovery. So here we're talking about data backups and restore point-in-time recoveries, ensuring that your data is replicated to geographically diverse locations and being protected against site-wide failures. And then another important aspect to Postgres high availability is monitoring and health check. So you want to be able to monitor the database health and performance metrics to detect and address issues before they lead to downtime. And one way to do that is through Prometheus exporter, and then there's also write-ahead log exporter as well, and we'll briefly touch upon that as well. But these are the things that you need to consider when you're thinking, okay, what does Postgres high availability mean to me? Okay, so let's briefly touch upon Postgres operator, which is a Kubernetes operator to manage high availability Postgres deployments that are built on top of the Patroni system using Spilo images. The Patroni is a system to implement a specific template for Postgres high availability. It comes with some tooling. One notable one is the Patroni CTL and a lot of scripts that allow you to do a lot of operations in your database. In addition to the operations that Postgres operator can manage declaratively. And when we talk about Spilo is just a container image that prepackage both Patroni and Postgres in the same image. So each one of your pods will contain both of those applications. And it comes with its own configuration, environment variables, and scripts. And again, this is done so that your job as an operator is as automatic as possible. In terms of how operator works, it defines custom resource definition, which is a spec to manage deployments of like Postgres databases on a Kubernetes cluster. And a notable about Patroni, it utilizes a distributed configuration system for cluster coordination and configuration. And this yes can utilize various backends. So for example, Zookeeper, etcd cluster, or by default with Postgres operator, leverage the metadata of Kubernetes objects to manage the Postgres databases within a Kubernetes environment. And hopefully this will become a bit more clear once we have a look at the diagram. And yes, sorry, I didn't mention it in this, but Patroni does support console. Right. So looking at this diagram, starting from the user's point of view, the user deploys and defines a PostgreSQL custom resource manifest. The Postgres operator that lives in your Postgres operator namespace detects this new manifest and by watching the Kubernetes API through control loop mechanism. And as soon as it detects it, it starts creating a bunch of resources associated to manage and create a new database. So those resources are a stateful set that contain your pod or pods, depending on whether you've set up replication. And each one of those pods will contain Patroni and Postgres. So as mentioned before, this is possible by running the Spillo image that has both of these packaged together. The Postgres operator pod also creates and manages a service that one or multiple services that are associated with a stateful set, and it also manages the Postgres cluster secrets for users and passwords that are associated with your database. The client, your client app, and in our case would be the graph node, would communicate with the Postgres database to do reads and writes via the service and endpoints. Some notable things here. So once the Postgres service has been created, the endpoints object is automatically generated to map the service to IP addresses of those pods. And the endpoints object information is part of the service's metadata, which keeps track of the pods that fall under the service's scope. In terms of replication here, when we have multiple pods with multiple replicas, Patroni updates the leader key in the Kubernetes object metadata file to reflect which pod is the master or the leader using the endpoints object. Now, this diagram is simplified. It doesn't show all of that replication. It just shows the different objects that the Postgres operator would create. But before we look into more replication and high availability, I want to first take a moment to ask if there's any questions so far. And if there aren't, I'm just quickly scanning the chat. Yes, tuning is done through the values.yaml. Some of our documentation includes some examples of certain options. I can show that in a moment. But I have a few more things to mention about Patroni. So as I said, in terms of any tuning tools that pair nicely with it, I was aware of a couple. Let me just quickly find it. PG, I think one of them is PG Tune. So is this. I'm not sure if it pairs with it, but you can check your configuration. Okay. I see others are writing, so I'll continue and okay. So in terms of Patroni, so a few more things to mention. The Patroni instance updates its stateful, as I said, in Kubernetes object metadata, and that status includes health and election participation and who is the leader key. Also, these Patroni instances keep track of each Postgres instance status to manage failover and leader election. And upon electing a new leader, the Patroni adjusts the configs as necessary in real time. And some of this is achieved by dynamically managing services and endpoints. In the event of a leader failure, Patroni conducts a new election and instances update their status. And while the above example mentions Kubernetes, both Patroni and Spillo are available to be used in any containerized environment. So Patroni can be deployed as an agent on its own on bare metal servers as well. So as Carlos says, that tools such as pgtune, you basically run them and they spit out proposals for your PostgreSQL parameters, and then you can take those and apply them to your configuration under values as part of your custom resource manifest. Managing huge pages needs to be also part of your pod spec, and maybe it would be useful to so there's a example that Chris shared with a complete Postgres manifest, but it might be useful to quickly show. So if we go to Launchpad namespaces, graph, and then under common, you'd have a graph database. So the two databases that are needed for running graph nodes are the subgraph data database and the indexer. And here you have an example as well of that PostgreSQL CR with the various parameters. And this is the default that comes with the graph namespace, and then you can override on write any of these fields. So for example, so we have added a guide for Postgres. Let's see if it's loaded. PostgreSQL. This is still under development, so please bear with us. But if you wanted, for example, to take the base definition of one of these databases and overwrite any of these fields, so for example, number of instances here, you would do that by adjusting, by adding this into your Helm file. All right. Going back to the presentation, loving the the chat, so please keep it coming. So this is Patroni and its role on high availability. Hopefully in the next diagram, it will become a bit more clear. So if you're considering the Postgres operator, you have a brief idea of how different objects are managed by the Postgres operator. But if we take a step back to discuss stuff like data integrity and consistency across different database servers, we do need to look at write-ahead logs, base backups, replicas, and clones. So in this particular diagram, you have two environments for managing your databases. The first one is your production. So your production Postgres cluster that in this example is comprised of one primary Postgres replica, one primary database, and two replicas. The primary database is the database that reads and writes, and then you have the replicas that read from your client app if set up to do so. Again, each pod, like the previous diagram, would run Patroni and Postgres, and all of these pods would be managed by the same stateful set in this diagram. If you're wondering how the data is replicated between the primary and the replicas, this is done through write-ahead logs, which means that instead of writing changes to data pages immediately, changes are first recording in write-ahead log files, so a detailed journal recording that of every database transaction and replica, the database transaction and change. So the data between the service, so between the different servers, so primary and replica here, is done to write-ahead log streaming replication, which allows for those logs to be streamed in real time or near real time. In terms of the different roles the primary runs, the primary is also in charge of sending rotated wall files via the archive command to object storage or local file system if that is set up to use. And it also sends base backup via a tool called WallG, which is a predecessor of WallE. So the wall files together with the base backups allow you for being able to have point-in-time recovery and also for failover processes. Now, in this diagram, there is a secondary system or environment named clone. This is named a clone because it is a way of creating point-in-time recoveries. You do this either by freezing the data directory and sending it to the primary of your clone system, or by pointing to object storage and using wall files and base backups to send data. This system would not contain live data. It would only contain that point in time data, and you would use this for testing, for upgrades, or for development. All right. Another example of a setup would be with standbys instead of clones. So the big difference here between the two diagrams is that the second environment is is a standby environment that is initialized from the primary data directory, but is continuously maintained via wall streaming. So even though it doesn't accept reads and writes, this system is replicated. It has all of the data replicated in real time or near real time. And again, another way of achieving this is through base backups that are maintained by replaying WAL files as well. You can think of this as a standby cluster that's allowing replication from production. And say a catastrophic event happens and your production system here fails, then you as an operator have the opportunity to manually move the traffic from this production system into this standby system, which is sometimes referred to as a warm standby. Right. Now, if we talk more about in terms of no hot standby for Matthew, so the hot standby would be the replicas here. The terminology would basically apply as so warm standby is something that just sits there with all of the data, waiting for it to take over your primary system, whereas the hot standby is something that accepts reads while accepts reads. So your replicas act as hot standbys in this scenario. And if you have a look in your so if you've deployed with the Postgres operator and the Spillo image, you have this command, Patroni ctl edit config, that shows you the definition of your current config. And I think I saw somewhere the hot, maybe it's not here, but somewhere there's here hot standby zone. What this means is that the replication between your primary and your replicas is done by a hot standby. Yeah, okay. Okay, so let's talk a bit in more details about write-ahead logs, because there's a lot to know here. The way it works is that instead of writing changes to data pages immediately, changes are first recorded in these write-ahead logs files. And this allows for commits to be atomic. And by atomic, we mean that each change is indivisible. So if a write hasn't been completed fully, there's no partial writing. Instead, there's a revert of that specific transaction. So in case of a system failure, the database can be rebuilt by replaying these entries. And this process ensures data integrity and data safety by maintaining a consistent state. When talking about high availability, it's important to consider archiving the write-ahead log data, so we can support reverting to anytime instant, as shown in those diagrams. And we would do that by installing a prior base backup of the database and by replaying the write-ahead logs as far as the desired time. Another important thing to note here, and after we do the lifecycle of WAL file, we can have a discussion. things to know about WAL files. So their default size is 16 megabytes unless otherwise configured. And the first step in the lifecycle is creating the file as needed when a new transaction occurs in the database. As new modifications are made, entries are written to the current WAL file until that WAL file is filled. When the file is filled, Postgres switches to a new WAL file. And the old WAL file, once it's been persisted to disk, it becomes a candidate for archiving. If there is no replication or archiving, the filled WAL files can be discarded in order to minimize disk space usage by deleting the old WAL files. If the WAL archiving is enabled using the archive mode on and the valid archive command, Postgres does not discard these filled WAL files immediately. Instead, it copies them to the specified archive location. So this can be object storage, local file system, network file system, and a few other options as well. Important to note here about the Postgres operator and Patroni, the archive mode is set as on by default, but it is ignored if there isn't an archive location set up and specified. So important clarification that Carlos is making about Postgres. So standby server does not accept connections at all by default. The term hot standby is used as a configuration parameter for a standby, which makes it accept read-only request. But failing over to a standby won't be done automatically. And replicas, on the other hand, accept read-only requests by default and can be promoted to leader automatically whenever needed. And as shown in the third diagram, a standby can have replicas of its own. All right. Anything thinking of what else to mention here? I think, the most important bit is that archive mode is on and it is ignored if a specified archive location is not used. Then in a replicated environment, any standby servers fetch those WAL records through streaming replication or file-based log shipping. And again, those WAL files are retained until all standbys have applied those changes, ensuring database consistency between the primary and the replicas. The retention of WAL files is additionally managed through settings like WAL keep segments, replication slog configurations, or the backup tools retention policy. So PG backrest or something like Barman. These settings ensure WAL files are kept as long as needed for failover, replication, or recovery purposes. So once the system decides that a WAL file is no longer needed for crash recovery, replication, or archiving, Postgres can safely remove that file. And here is something really important to know, is that in the event of replica experiences a failure, the WAL files will be retained and not deleted until either the replica has been successfully recovered or removed. This is really important for ensuring data integrity, but it's worth noting that if you, so say you lost a replica and you think, okay, I'm gonna wait for a few days, I have time to recover this, you need to be aware of the fact that this WAL file retention can lead to rapid disk space consumption, which poses a risk of exhausting available storage, which can bring down your primary as well. And before moving into detailed gotchas, I want to take a moment to encourage discussion. I see here a question from Matthew. Any performance hit with wall enabled? For example, if graph node will be slightly behind. Yeah, important to note, wall is not optional, so Postgres has no other mode of operating. Even on a single instance with nothing else going on, Postgres works by writing wall files first and only then committing to the persistent data directory. But propagation to replicas will incur a delay. I see here Matthew saying a second is not a small window. Indeed, but my understanding is that Postgres works this way because it prioritizes data safety above all else. While other people are typing, I will continue with the gotchas, but please keep them coming. Carlos saying that before streaming replication, the typical window was more like 1 minute. And there is the option of synchronous replication, but that will incur a performance penalty. So synchronous replication means the data from the primary is persisted immediately to the replicas, and database changes are not confirmed until replicas have those changes as well. By default, the replication between the primaries and the replicas is done asynchronously. To Matthew's point of data safety is not necessarily the number one priority for us, given we're indexing blockchain data. That's true, but this is the only database that the graph node supports. I think that's correct, right? Yeah. Okay. So it's by design. All right. Continuing with the gotchas. So something that's important to note. So graph node query nodes. You might think, okay, I will set up my query nodes to read from replicas only. It's important to be aware that they require write permissions to write SQL migrations. And therefore, when you set up your stores in your graph node query nodes, you have to set up your a connection to your primary database for running those SQL migrations, and then connections to your replicas for handling read requests. So that is one thing that wasn't necessarily, yeah, that's the first thing. And then there's the weight field here. So in this case, having weight 1 and 1 for your different replicas means a 50-50 load between the two replicas in terms of read requests. And other gotchas. So when starting a standby from S3, access secrets can only be passed by environment variables. And those environment variables look the same as when setting it up from a primary, but they have the standby in front of them. And this will be better documented in our documentation. Now, if you want to start a clone or standby, and this new instance will have its own S3 bucket, but you're using another bucket as the source. Credential for those can be passed on with environments variable. So again, they look similar to the regular ones, but with clone and standby prefixes in front of them. Another important gotcha, standbys will not use SSL to try and contact the existing source instances. So you will have to change PGHBA setup on the standby user to allow connecting without SSL. And setting up a standby is a one-off init process. So if you interrupt it, it needs to start again from scratch. When you're establishing a standby or a clone with streaming capabilities from an active instance, it needs to possess all of the access credentials from the originating instance. I think this is actually a duplicate of a previous point. When you're taking a base backup from new replicas, standbys, and so on, WAL files accumulate at a fast rate and exhaust disk space. So again, beware of that. That's another gotchas around WAL files. So for as long as a base backup is in progress, WAL file continue to accumulate. For monitoring purposes, there is the Postgres exporter that runs great out of the box, and then there is a WAL-G exporter that collects metrics around the write-ahead log performance and how fast they're accumulating and so on. So important to know here that you need to set up additional volumes in your Postgres configuration to share the run etc path for the WAL-G exporter. Again, this will be clarified with a lot more details in the documentation. And then when using object storage for WAL archiving, by default, the operator expects that the bucket endpoint follows the DNS style naming convention. So if you're using AWS for S3, that's great because AWS already follows the DNS style naming convention. But if you're using object storage that follows path style naming convention for buckets, so Ceph is an example of that, you need to pass this environment variable, so AWS S3 for path style, to the Postgres operator config map. And talking about timelines is an important concept in Postgres. A new timeline is initialized following each failover or switchover event. So while replicas are generally synchronized with the primary, there are operational anomalies that happen, and those can lead to diverging timelines if instances inadvertently receive writes simultaneously. So this is managed to timeline history functionality. But what's important to know here is that when you are deleting a stateful set pods that may hold unarchived WAL files, this could result in data loss from the cluster given due to this timeline functionality. The next slide is some resources. So a link to the WAL-G exporter, Postgres exporter, the Patroni, Spilo, and Postgres operator. There is one issue that is worth noting about replication and graph node. That is here. I will copy it for everyone. Yeah, when graph nodes uses a shard that has asynchronous read replicas, query results are not deterministic because the read replicas can trail behind the main database. So asynchronous read replicas are the way to do replication by default, unless you set up synchronous replicas, which are a lot slower. So there is no solution for this, but it's worth knowing. All right, I'm gonna stop here and invite everyone to ask more questions, discuss, tell us what else can we cover, how else can we help on this high availability.
I think it's worth just saying on that issue that you had up there for a moment, Anna, um, because at least, I'm actually following up with David internally just to get a better idea of what the mechanics or internals of this are. But if indeed using replicas basically breaks query determinism, then this is not a configuration that anyone should be using on the decentralized network, because returning a non-deterministic query result would open you up to a query dispute. Um, so it's definitely worth saying that we should get a bit more clarity on the state of this before recommending this configuration widely. Yeah, it won't be a POI problem. The POIs should have no problems. But there's an attestation linked to the POI that is generated for a query. And yeah, I guess I can only infer that David is saying that there's some, like GraphNode in the processing of a query is kind of obtaining data from both sources, and they, may not represent the same snapshot of the database, and so there's some inconsistency there. This is all reads. Um, but yeah, without, understanding exactly why this issue, um, like exactly what the mechanics of why this issue is true, we can only kind of speculate. Um, but in theory, I don't see why GraphNode couldn't be adjusted to query, for all of the components of data that it needs from the same replica source as opposed to the master. Um, and yeah, I guess we'll as progress on this becomes clear, we'll be sure to update everyone.
Have you tested the new GraphNode pane? Okay. Sorry, Kurt Node released. Um, where is everyone with, so Matthew and Pinax, you guys have said that you are exploring the Postgres high availability. Where are you in this process? It'll be interesting to know. And also, I see Sam from Semiotic here, wondering if you have, like, if you are doing anything high availability related with Postgres. It'll be good to get a view of where everyone is.
Oh, for Postgres, I'm not doing it in Kubernetes right now. I'm sharding Postgres and testing it with different. That's kind of the use case I'm going for, is having JIT off on the primary, um, so it indexes very quickly, and then having a streaming replica that has JIT on. So, and then Graph Node will go to the replica for queries. Obviously, you could further tune that to say only long form queries go to the replica, which would probably be even better. But it's the most fast solution I could think of as far as getting the best of both worlds, where you're, indexing extremely quickly with JIT off, but still all maintaining all that data quicker, and then getting the long form queries. I'm using streaming replication, which was basically just copying over the DB to the replica in a fresh Postgres directory, and then basically syncing those up. Just running a post PG base backup. Yes, basically a PG base backup, and then it hooks those two together, and then you basically just right now just run graph node queries to the replica, and then that way you get the best of both worlds. Because I don't know if you've ever turned JIT off on your Postgres while indexing, but it is a massive speed boost.
I don't think we haven't explored that at all. But that's good to know. We can look into it further.
Yeah, just if you do, it won't mess up your database. I've done it a bunch of times in testing, but testnet obviously if you have precautions. But yeah, if you do that, you just watch your Grafana. The indexing speed will shoot up. I believe Pain has done it as well early on. Yeah, I believe Pain has tested the JIT off thing as well. But that's kind of the best of both worlds I can think of, where you get the massive increase in indexing speed, especially for big subgraphs. But with JIT off, it's terrible at long form queries. So the ideal candidate, I think, would be, further tuning the your Postgres and Graph Node to only send long form queries to the primary, um, or the replica, and then everything else, it doesn't really matter. Okay, it looks
Thank
like
you.
I got it correct.
This is great to know. We will review this and see if this is something we turn on by default in the graph node namespace as well. But yeah, this is great. Thank you for sharing.
Yeah,
The alpha.
because
So yeah.
that's why that's why I was asking if you could tune the replicas, um, because that's kind of like, otherwise, like Chris said, you'd have to spin up a whole other Postgres cluster that talks to that cluster, so you could have different values, which is kind of a bummer. Because, well, I guess kind of, but you're gonna have just way more stuff. Fill images and still leverage Patroni.
That's for containers. So instead of deploying on bare metal using LXC containers with a Postgres image, you can use the Spillo image that contains both the Postgres image, the Postgres version you want, and the Patroni.
Yeah, because that's kind of like the alfalfa that I'm going for right now.
This has been great. Apart from doing documentation and looking into the option you mentioned, I would struggle to say it out loud because of my accent. I don't know why. Is there anything else we can do? Has this conversation been useful? Yeah. Any feedback basically is welcome. Awesome. This is great to hear. Just want to quickly address the fact that we will continue with another session on Helm charts. Yeah, we had a lot of content on this, and it just made sense to show this for this session. And it turns out it has been great timing with what Pinax is doing. I will shut up now so other people speak. I know I'm being awkward.
I have a question that I thought, but I don't know if it's possible. When building out a Helm chart, can you have stuff print out in your values YAML? Like, let's say I wanted to print out total RAM space or something like that. Can I have that print out?
No.
No. Dang.
I mean, not in the values file. Like the values file do not
yeah,
run that
but
kind of
put
logic.
like yeah, but put it in like the in the deployment or something like that, and have that logic in there. So like, I was thinking
That
like you could have it in there.
I think you can, in combination with the debug flag, like Helm as a debug flag. Like if you do Helm template or something like that, right? It's going to spill you over, spit over some stuff. So yes, you can do some tricks to get like to see values of variables or things like that, in combination with the debug flag.
Because I was thinking of using that to build out like tuning or something like that, where it just grabs everything from your machine and goes, oh, okay, here you go.
This
Put
is a bit of
logic into that.
different approach, what I linked, but there is an API that allows you to like basically inject certain pod metadata, including things like the resource allocation to the container or to the pod. You can inject that metadata into the containers in the pod as environment variables. So you would then have to do like runtime templating with those environment variables. But yeah, maybe.
Yeah, because I was kind of just thinking if you get like an army of machines, it would be cool to just have all those min limits and everything get based off of some other logic.
Yeah, and in this case, you would still be like configuring the workload. whether it's a deployment or a pod or whatever, with a
Yeah.
static, CPU, memory, and other resource constraints.
Mm-hmm. Interesting. Thank you for that.
You can make those dynamic, if you give your pod credentials to actually change the resource, right? You can have an init container that just goes log at what the resources are, generate some kind of changes you want to make, and then change the spec itself, right, on the cluster Kubernetes. But that's maybe not the most elegant thing to do. You basically need an init container that has access to the Kubernetes API and is able to change the spec, right?
Mm-hmm. I'm just basically trying to figure out ways, even though I've severely reduced any editing I have to do with making Helm charts, just trying to make it so I have to do nothing as much as possible.
I think getting the P2P node port set up in charts is an example of how we do that with the init container. Just gonna quickly find a link for that just to share it.
Yeah, I was actually looking at that's what kind of sprung that thought in my mind when I was playing with that.
All right, so you so you are aware of what I'm talking about, yeah.
Yes.
But I won't do that. I think you should go as far, or you could go as far as your pods as some type of RAM and CPU allocation, and then you have a script on boot that just looks at those and adjusts the Postgres config based on those. I wouldn't go as far as seems like not the right place to be doing that. You'll have your pods with fixed resources, and then the config to Postgres gets dynamically adjusted based on that. And then if you want to actually dynamically adjust those fixed resources, you should do that on another layer, right? Something that's running on Postgres, on Kubernetes, independent, and just for some reason changes those resources, right? I think that's a better separation of concerns.
Yeah, that makes sense.
All right, thank you everyone for coming. We will see you in 2 weeks' time.